So, chapter 3 was examining relationships, specifically examining linear relationships. So, to understand a statistical relationship between two variables, we measure both variables on the same set of individuals. And then, just in general, for the data analysis, you want to ask some general questions about the data and the set of individuals, like who are you measuring the variables on, what are you measuring, why, and then when, where, and by whom. So the two variables are the response variable and the explanatory variable. These are both going to be two quantitative variables. The explanatory variable is the x is like the x variable, and it explains and influences change in the response variable, and it's an independent variable. And then the response variable measures an outcome. It is the y variable or the dependent variable. A scatter plot is a graphical display of bivariate data that shows the relationship between two quantitative variables measured on the same set of individuals. So to interpret a scatter plot, you want to ask 4 questions. What is the form? What is the direction? What is the strength? And are there any outliers? So for example, what is the form? Is it linear, quadratic, exponential, or clustered? In this example, it looks like it's relatively linear. And then what's the direction? Is it Is it a positive association or a negative association? So in this example, there is a negative association because the above average x values occur with the below average y values. Strength is it. This has to do with the strength of like the linearity. Is it weak, moderately strong, or strong? And in this example, it looks moderately strong because the data points are relatively linear but not perfectly linear. And finally, are there any outliers? Are there any observations outside of the pattern? And in this example, there's no obvious outliers, but maybe suspected one at 5.5, 15 right here. The correlation coefficient measures the direction strength of a linear relationship. The R value is always between -1 and 1 meaning it is perfectly linear and positive, like in this example, and then -1 meaning it is perfectly linear and negative. And then when R is 0 or any fraction close to 0, it means that the linear relationship between the two variables is very weak and there is not much there's not much of any correlation between them. So as you can see, this one will show you that R is equal to 1, this one will show R is equal to -1, and this will be R equal to 0. The properties of correlation coefficient is there's no distinction between explanatory and response variable. Units of measurement do not affect correlation because R is based on standardized values. Both variables must be quantitative, and R is non-resistant to skew or outliers because R is based on means. And then this is the equation that you can find in the pink packet. The numerical summary for bivariate data gives you 5 values: the correlation coefficient, the mean of x, the standard deviation of x, the mean of y, and standard deviation of y. And this is how you can get there on the calculator. The regression line describes the relationship between an explanatory variable and a response variable. It is used to predict y for any given x, and y hat represents the predicted value. So again, this is the equation: y hat equals a plus bx. And then for extrapolation, this is just using the regression line to make predictions outside the range of x values, which is often inaccurate. And interpolation is estimating predicted values between known values. So the least square regression line, what is this? This is a line that makes the sum of the squared vertical distance of data points to the line the smallest. The errors for this line are going to be in the vertical direction. and this is because you're predicting y from x. The prediction error, aka or also known as the residual, is the observed value minus the predicted value, so y minus y hat. The line always passes through mean of x and mean of y, and the equation for this line is y hat equals b sub o plus b sub 1 x, where b sub o is the y-intercept and b sub 1 is the slope. And you can find both of these equations in the pink packet. And then also the coefficient of determination is just r squared. And this is the percent of the variation in y that can be explained by the least squares regression line or by x. To find the residual point, you do the observed y minus predicted y, which is the value found from the regression line by plugging in x. Positive residuals, this is when the point lies above the regression line. Negative residuals, this is when the point lies below the regression line. And then the sum of all residuals is equal to 0. So a residual plot, this is basically just a scatter plot of residuals against the x values. Y is always equal to, or y equals 0 represents the line of regression, and the x values are the same as they are in the, or as they are in the data, and then the y for the residual plot are the residuals. So, for example, these are 3 different residual plots. This one you can see there's no obvious pattern of the residuals, meaning a linear model is a good fit. But for these two, there is a pattern of the residuals, meaning a linear pattern would not be a good, or a linear model would not be a good fit. So correlation and regression wisdom, this just has to do with outliers. An outlier is an observation that lies outside the overall pattern. Points that are outliers in the y direction will have large residuals. So again, this is y minus y hat. And then these points, or points that are outliers in the x direction, will not have large residuals. These outliers are instead considered influential observations, which is an outlier that when removed, the correlation coefficient and the slope change dramatically. So all influential observations are outliers, but not all outliers are influential observations. Influential observations often have small residuals because the line of regression is pulled toward them. And then to check for influential observation, you must run the linear regression twice, once with the point and once without the point. And the point meaning the outlier that you suspect to be influential. And then you compare the two different r and slope b sub 1 values you get, and if there's a significant difference in the two lines, then the point is considered an influential observation. Lastly, we have lurking variables, and these are variables that is not being measured but may affect the relationship between the explanatory and response variable. If you're finding a linear relationship, for example, between mean number of TVs per household, which would be the explanatory variable, and mean life expectancy, which is the response variable, and the results show a linear positive association, you can't just conclude that a country should buy more TVs in order to increase its life expectancy. This is because of the lurking variables that affect the relationship. For example, a lurking variable like mean household income most likely influences this positive association. So this just tells you that association does not imply causation. And yeah, that's pretty much it for chapter 3.